this graph, you see the corresponding axis, Y and Z, right, that tell you about the number of ions produced per cm of the free path, in this electron impact ionization mass spec across with the energy in different gases here. So you have a formula where this capital I, the number of ions produced per unit time, in a volume V, right? This is given by the product of N. This is a proportionality coefficient depending on which program you have, and the P, the pressure, multiplied by the current in the system. Okay. So you see here, at about 70 electron volt, you see a Y maximum appearing around here. So you always peak at this, okay, for the three graphs. Now coming to the fragmentation of take an example of methanol, CH3OH. What happens is, first of all, you ionize it by removing one electron to make it singly positively charged. And then after that, you self-dissociate because this bond now is being weakened. So how do you strengthen it? You form a double bond, but in doing so, you lose an H, okay, for the oxygen to form a double bond here. So this H comes from a carbon. Now, another way is, right, you start with again your methanol. You can also cut this bond to give you the hydroxy radical electrons here and the methyl cation. So once you have this cation from the second equation here, you can continue to lose also the H atom. So the question for you is, why won't electron impact be suitable for analyzing proteins, a big biological molecule? As you can see, it's too big because it shattered so many different kinds of chemical bonds. Just now in the previous slide, we only used a simple molecule with one carbon, methanol, and you can see that there's really 4 different kinds of product. Imagine your proteins, 20 kilodalton. So in any given protein, you contain 20 different amino acids. So the EI, if you're using electron impact, it will shatter the proteins, not just the amino acid, but also within the fragments here, the R groups, even peptides. So the result is you have so many different permutations, it's too complex to analyze. More than 10,000 different signals from just one small protein. You don't want that. For chemical ionization CI, it uses a reagent, a chemical or an ion, to react with the analyte so that it can form ions, right, either by a proton or the hydride transfer. Okay, hydride is H minus, proton is H plus here. Both give you a product that's ionic. Now the reagent ions are produced by introducing a large excess of the methane, like CH4, into the EI as a source. So methane is the reagent gas, but methane in this case is unreactive inside, but you're going to charge it. So what you want is to derive a CH4 plus and CH3 plus and CH2 plus. Then you combine with the methane to form a CH5 plus and a C2H5 plus, okay, your ethyl cation. So the mechanism goes as follows: bombard with electron, remove electron pair because electrons have spin, so they can pair up. You form a CH4 methane cation. Then it undergoes a dissociation to form this trivalent CH3 plus, H atom removed. Here can also remove H2 gas due to entropic reason, CH2 plus form, and then you form these other 2 ions. Now for C3H5 plus ions, right, it's formed by the successive reactions. So first you combine the CH2 plus and CH4, and then you get C2H3 plus, removal of H2 gas and H atom, and then again it propagates, right, reaction again with the high concentration of methane to form the C3H5 plus ion. So you can see, right, if you analyze methane, ionize it with plasma, 20 Pascal, these are the relative intensity, okay, and the identity of the ions using the MZ ratio. So in this case, we have proton transfer, right? H plus from here goes there, H plus transfer. In this case, the hydride transfer H minus goes over and then N become N plus. Look at the charge balance. Now let's continue here. Ammonia is a reagent gas, right? Because ammonia is a base, you abstract protons. So you see if this is the reagent gas, it absorb, right, the H plus, right? Then this become, look at the color, become NH2. In this case, it can also combine, right, in tandem here to form a overall positive charge. So the use of ammonia allows for proton transfer. Or ammonium, the amine form, you give off the protons. Again, you want to form charged particles. So here are your signals. Okay, 200 microbar. Next, Fi, field ionization uses very strong electric field to produce ions from gas phase molecule. Look at the power again. Okay, the energy is 70 electron volt. So for field ionizations, the energy transferred to the Fi process is a fraction of 1 electron volt here. Okay, see a difference between the EI and Fi. The difference comes in, right, in Fi is not so powerful because you don't want to anyhow hunt time and fragment it. You only see, okay, a bit of energy and then you see the signal here, okay, only here. But if you go to EI, right, it's much stronger for 70 electron volt. So if you bombard, you can have different kinds, so many different fragments, right? You have different signals, more complex. And now here in this case, we have more than 10 carbon in this molecule of analysis. It's ester. So methyl stearate. So depending on analyte, you may want to choose Fi over EI. Okay? Because Fi is weaker, you look at the energy amount, you don't see much fragmentation. So back to our different kinds of ionization method. Here we talk about soft IM, nitrogen laser, a 337 nanometer UV laser. Ooh, the surface is a MALDI. Cyanohydroxycinnamic acid shoots up this aerosol, this very little small fragment. ESI, you put the fluid, right, without any additive ionic compound here, it just through a very small orifice and it shoots up because the charge, right, it like to repel each other via this gold tip needle, ESI. So soft ionization technique keeps the molecule intact. Don't want to break only bonds. Electrospray ionization first conceived in the 1960s by Malcolm Doe, but a professor at Yale by the name of John Fan, right, translated into practice and more research in the 1980s, and he was afforded the Nobel Prize. Sometimes in life it's not about being the first, but who continues it and even ends it. For MALDI, it was first introduced by a scientist called Franz Hillenkamp in 1985, before you were born, and Michael Karras in Germany, Frankfurt. And it was made possible to analyze large molecules by inexpensive mass analyzer like the quadruple ion trap material. Take note here, it's not even the QTOF, not the QQQ, just the quadruple, just the ion trap. Today we have the QQQ, QTOF, the triple quadruple. Laser ionization, LIMS. So, LIMS, laser ionization, mass spectrometry. The laser pulse ablates material from the surface of a sample. Then you create like a microplasma, ionizes some of these sample constituents. And then it does both job of vaporizing and ionizing at the same time. But the thing is, some of these molecules don't absorb laser energy efficiently, right? So maybe just buzz and go, doesn't absorb. So therefore, we need to apply some kind of matrix to help it absorb the energy as a whole. Therefore, there's the invention of MALDI, which is one of the more popular mass spec. Matrix-assisted laser desorption ionization, MALDI. 337 nanometer UV laser onto the surface with matrix of this cinnamic acid and cyanohydroxyl, shoots up these little particles. And we can do a high throughput spotting on the MALDI plate because you see many positions, right? You can do at the same time. Your targets are just ingrained, okay, on the surface of this plate. How does it work here? So you have absorption of the UV radiations by the chromaphoric matrix and then ionizer matrix. So analyte on the matrix plate, shoot laser. Dissociation of the matrix phase into very highly compressed gas, and they have charge transfer of the analyte because you have this expansion of the matrix, right? So you need to escape. So now they will explode, it will pop. Okay, too much pressure, too much surface tension. You need to relieve it. So in this case, you have got the acidic matrix full of H+, you create more positive ion, which means also there's a charge repulsion and want to escape. This is a good thing here because when it can only promote the positive ion, that means the negative ions will be filtered out, so you don't have a mix of its ions, which means if I have both cation and anion, there may be reactions and you lose some of this cation detection. So for MALDI, it generates a spectra with just a singly charged ions. There won't be a doubly charged ion. There won't be a triply charged ion. Unlike ESI, there's a possibility of a bivalent 2+, or even an AGB 3+, unlikely 4+, but MALDI strictly singly charged. Positive mode is about, M plus H+, your acidic proton, right? Negative mode, you lose hydride using the basic medium. MALDI is more robust ESI because it can have some tolerance towards some salt, ionic compound, and non-volatile components. Come on, after all, it's a matrix. Easier to use and maintain, also high throughput as you have shown, and also require a very petite amount of sample, small little liquid, 10 microliter of a 1 picomole per microliter sample. And the principles for this MALDI-TOF time of flight mass spectrometry. So from MALDI in the sample, ionize, laser shoots it, sample goes over, ionize, vacuum, time of flight, let them fly, detected. Few cuts of laser. Okay, some shorthand, and this element in the periodic table, neodymium is magnetic, erbium, YAG, YAG is yttrium, aluminum garnet. So you see different kinds of laser, in which mode the UV range and the IR range, depending on the wavelength, different energy, of course, the higher the frequency, shorter the wavelength, and shorter the wavelength, higher the energy. So with different energy, you can also lower down the pulse width, okay, shorter, okay, more energy. Now the principle of MALDI. So we need to establish the time of flight, right? Ion. How do we convert into some signals that we can see and visualize? Okay. Based on the accelerating potential, it will give the ion a charge of Z corresponding to energy of ZV multiplied together. And then we equate them to the kinetic energy of this ion, half mv squared, and of course m is the one you're interested in, mass, right? M, the Z is not this Z, the Z, so it's +1, so it's mz ratio. So now we do some simple translation of the formula. Because velocity is length, right, of dimension over time. So then your mz, you divide, is what you get. But the v and l here, you cannot measure using enough accuracy inside the MALDI, inside the mass spec, right? It's not a piece of ruler you can just measure by eye. So we can use another form by the time of the flight. Time of flight. How the time taken to be in the air, not air but vacuum, not touching any ground. So we have some constant where we need to calibrate depending on the mass spectrometer. A and B is a calibration constant, right, for a particular mz value. So how do we measure, right, the TOF, the time, okay, small t of the ion? And then after calibration to find A and B, then we can convert to the mass and you can find an mz value. Next, then we store this B term over V. Again, because the V is not always consistent, but there's some slight changes. So we need to correct for these variations in B. Now, if you change the voltage, right, so it doesn't affect the calibration much. Now, of course, it works under the assumption that all the ions have the same kinetic energy. Okay, again, assumptions. What are some consideration? The samples are all loaded to a metal strip for analysis. Just now you saw the high throughput, different positions. And a sample of concentration of 1 milligram per ml is the best, not too concentrated. And it's usually 1 to 10 picomole of the sample required. Once again, if you have too high the concentration, it might get very messy. And that's the purpose of mass spectrometer as well. You don't need a lot of sample. You want a small bit to just test you analyze the structure. Then you see, okay, is the synthesis correct? For this step synthesis, this is the right structure. Let me continue the synthesis using these steps and start from step 1. Ooh. So after, with this small amount, you spot it on the sample position right on the metal strip, and then with 0.5 microliter of the matrix, normally the concentration is 10 milligram per ml, okay, to here. Just let it dissolve in the matrix. And there are many kinds of matrix used for the MALDI-TOF. Some include this cinnapic acid SA for protein samples, or alpha-cyano-4-hydroxycinnamic acid, ACH for short, or peptide sample. And the 9:1 matrix of the 2,5-dihydroxybenzoic acid, and 2-hydroxy-5-methoxybenzoic acid, SDHB, or carbohydrates. DNA, you can also analyze using this MALDI-TOF by using different matrices. So if you have a new sample, you need to try these different matrix and see what works for you. Again, experimentations, researchers test, hypothesize, okay, safe, good. Some precautions. When you prepare the MALDI, the sample should be free of sodium sulfate. Okay, it's charged and it's long chain. It shouldn't be radioactive. Best to remove the buffer salt and detergent, okay, by dialysis, removing before the analysis, and then dissolve in the solvent, trifluoroacetic acid in water, so it doesn't degrade the sample. What happens when you have too much salt? Salt, for instance, KCl, K plus can be detected. So the signal, because they are metals, salt, right, metallic or ionic, the signal becomes so strong, so the relative signal become noise. Okay, so you don't have a good spectrum. Okay. But note that if your concentration of TFA is more than 0.1%, what happens is it can cause ion suppression, because again you can accentuate your other peaks much higher. More to be careful. If it's not possible to remove these contaminants using this TFA in water, using the salt dialysis, then you should prepare a sample at high concentration. Then you can also dilute the sample until where the contaminants, which should be at a lower concentration than your sample, have lesser effect on the spectrum. So either you dilute such that your contaminant becomes so little that it doesn't affect it, or you can remove it. The level of buffers and detergents, but take note, not SDS, which exceed the volume limit will probably cause the spectrum to degrade. So once again, you either have a not very reproducible spectra, that means every time you scan the sample, you have all different kinds of relative intensity and more signals. Can't be sure. So in general here, for this kind of salt buffer, do not exceed this concentration for each of them. Another diagram, more colorful this time. Ion source charged. Again, we have some space, time of flight, detector, Okay, these are just a schematic color schema. How do we increase the time of flight? The longer do you run, the better it separates, right? So we turn it, but of course you can't have so long like this tube here. Lab also has lab constraints, so we do a reflector. Pew, we have a longer pathway detector. Okay, so you see now the peaks are resolved. Here I'd like to introduce to you something called the SELDI, SELDI, Surface Enhanced Laser Desorption Ionization. So this is trademarked as a protein chip, especially for protein analysis, used for proteomics. Sample goes directly to this protein chip array, okay? And then this protein are captured, retained, and purified directly on the chip. So not just analyze, but then you retain there, purify from there. So instead of just using this plate as a platform to put your sample for analysis, but here we continue to work on it. So when we use this protein chip array plate, right? So it's being read by the SELDI. Not only we can detect and we can see the molecular weight differences, but we also continue to use the sample and take it out. So here's the difference. Take a look between a normal spectra here and the one with tumors. Here you see distinct signals, right? It's double twin peak here. So potentially, when you combine your MALDI SELDI, you can see some difference in the sample. Here's some practice questions here. You have your mass spectra of your 1-pentanol and ethyl acetate. Both have the MR of 88. Which of these mass spectrum correspond to 1-pentanol? And what are the fragments for the MZ 87, 31, 73, 45? So try to write down the identity, write down the formula of the ions, and also maybe mechanism how it's being formed. Okay, so take some time to work on it, and once you're done, put in the comments below here, type it in, and then we'll go through. I'll also comment on it, give you a response. This is normally tested. Another question is, what is being transferred in the following reactions? You see the H, right? In this case, it's colored, but in exam, I don't think it's colored. H goes over, is it hydride? Is it cation? Tell me. For a carboxylic acid, which mode of ionization will be more suitable? You have learned a few, and you see the merits and pros and cons, demerits. Which is better? Carboxylic acid, your R, COH. Alkyl, COH.